Welcome students. We are back with another lesson. In our previous class, we have discussed about binding energy curve. In your binding energy curve, along the y-axis, we plot the binding energy per nucleon versus the mass number. Now, in your binding energy curve, we have discussed about this lighter nuclei. The lighter nuclei like your deuterium and your lighter nuclei like tritium. These lighter nuclei, they have low binding energy per nucleon as compared to your other elements. So your lighter nuclei like hydrogen, deuterium, tritium, they have lighter binding energy per nucleon. So if they have a lighter binding energy per nucleon, that means they are bounded with a less amount of energy, or I can say they are loosely bound. Now, if they are loosely bound, that means they are unstable nuclei. So, so your lighter unstable nuclei like your deuterium and your tritium, just consider example like your unstable lighter nuclei, your deuterium and your tritium. In order to attain stability, what they do, they combine to form a stable nuclei. Fine. Now, in the process of forming a stable nuclei, that is, they form a element, whose nucleus is stable, like in the case of a helium atom. Along with it, it releases some other nucleon particles. Right? So you had two lighter unstable nuclei. This unstable nuclei combine to form a stable nuclei. Now this stable nuclei later forms a further stable nuclei and release the higher binding energy per nucleon as some energy. So this is what happens in your nuclear fusion. Your two lighter nuclei are fused together to form a stable nuclei, like in this case your deuterium, your tritium. They are fused together to form a stable nuclei helium. In this case, the deuterium has two nucleons, one proton and another neutron. Your tritium has three nucleons, that's why three, one proton and two neutrons. Now they combine in this case. So how many protons will be there? One proton, two protons. One proton, two protons. How many neutrons? One neutron, two neutrons, three neutrons. So how many neutrons are there? Three neutrons. Now in this case, this is still unstable. This is a heavy nuclei but unstable. So in order to attain the stability, what it does? It releases some extra nucleon. Can you see? It has given away the extra neutron in order to achieve the stability. So you have two protons and two neutrons. Now this is a nuclei of a helium whose mass number is 4. Mass number means the number of nucleons is 4, in which there are two neutrons and two protons, and the extra neutron is released. Fine. So in your experiment, the deuterium and your tritium, they fuse together to form a stable nuclei of helium atom. Fine. Now, one more thing you notice is that the deuterium has two nucleon. The tritium has three nucleon. Fine. So your initial elements had how many nucleons? 5 nucleons, 2 protons, 2 protons and 3 neutrons. And what is the final product? The final product is your helium. In case of helium, there are 2 protons and 2 neutrons. Apart from that, there are 1 extra neutron. So here they had in total how many protons you had? 1 proton, 2 protons. Here it is 2 protons in the reaction. Fine. Apart from that, it has 1 neutron, 2 neutron, 3 neutrons. You had 3 neutron. So look at the product side. In the product, there is 1 proton, there is another proton. So how many protons? 2 proton. Fine. And how many neutrons? 1 neutron, 2 neutrons, 3 neutrons. Fine. So this is an example of a mass conservation. The amount of the mass which went into the reaction is equal to the same amount of the mass which came out of reaction. Fine. So this is your mass conservation. Fine. And this figure shows the example of a nuclear fusion. So what is a nuclear fusion? Nuclear fusion is the process in which the two light nuclei combine at extremely high temperature to form a single heavier nucleus. This process is called as your nuclear fusion. Fine. So let's take an example. Suppose you have a deuterium and you have another deuterium. These two are lighter, unstable nuclei. Your deuterium has two mass number. That means one is your atomic number. This one represents the number of protons. So how many proton? One proton. But the mass number is 2. That means the other nucleon is a neutron. Similarly, in this case, you have a proton and a neutron. So these are your isotope of hydrogen atom, deuterium and deuterium. Now this deuterium is unstable, so they fuse together to form a stable nuclei. In this case is your helium atom. This helium atom has a mass number 4 and atomic number 2. Atomic number 2 means 2 protons, 1 proton and second proton. 4 means there are all in total 4 nucleons. So if there are 2 protons mean there will be 2 neutrons. Along with the stable nuclei, in nuclear fusion you also release a high amount of energy. Let's take a few more examples. Suppose you have a deuterium and you have another deuterium. These two deuterium fuse together to form a heavier stable nuclei. This is a isotope of a helium having mass number 3, atomic number 2, plus you have 1 neutron emitted plus 3.27 mega electron volt. So what is happening in this reaction is you have a deuterium. In deuterium you have 1 proton and you have 1 neutron. Fine. These two deuterium fuses together. When they fuses together, they form a heavier nuclei. In this nuclei, you will have a two protons and two neutrons. Now this heavier nuclei is slightly unstable. Therefore, it further disintegrates into a stable nuclei. The stable nuclei having two protons and one neutron. Along with this, it emits one neutron and some large amount of energy. Fine. So this is deuterium, this is deuterium. They fuses together to form a heavier nuclei. This heavier nuclei further disintegrates to form a stable nuclei, which is the isotope of a helium having mass number 3, 1, 2, 3. Along with this, it emits one neutron and some energy. Fine. Now, the important point to note here is that the mass number of the stable nuclei in this case is how much? 3. The mass of the stable nuclei is lesser than the sum of the mass of the two unstable lighter nuclei. So in this case, how much is the mass number? 2. In this case, how much is the mass number? 2. So 2 plus 2 is how much? 4. But you are getting a nuclei which is having a mass number 3. So you can clearly see the mass of the stable nuclei is less than the sum of the two lighter nuclei. So what is happening to the mass here? Now here you notice there is a mass defect coming into the picture. This delta M is being converted into the extra energy which is being emitted. And how much is this extra energy? 3.27 mega electron volts. And how can we get this energy? We know energy E equals to delta mc square. So this extra energy is coming from the mass defect. Can you see? Fine. So similarly, in your second example, you have a deuterium having one proton. In this case also a deuterium having one proton. In this case So in your second example, you have a deuterium which is having a proton and a neutron. this deuterium, which is having a proton and a neutron. These two deuterium are fused together. If they are fused together, what happens? They form a heavier nuclei. This heavier nuclei has two protons and two neutrons bounded together. Fine. So when these two deuterium are fused together, they form a heavier nuclei. This heavier nuclei is unstable, so it disintegrates into a tritium. This tritium has one proton and two neutrons. Further, it disintegrates into a hydrogen having one proton, and it releases some energy. Again, in this case, look at the reactant side. In the reactant, you have two protons and two neutrons, isn't it? One proton, one proton, one neutron, one neutron. So what is the total mass number? 4. In the reactant side, look at this stable nuclei which is formed. This stable nuclei has a mass number of how much? 3. One proton and two neutrons. Fine. Again, there is a difference in the mass coming into the picture. This difference in the mass, delta M, this difference, the difference of the mass of one neutron, what is happening? It is being converted into the energy. Fine. So you can also understand it like this. Suppose that unstable heavier nuclei had the two protons okay, so you can also understand like this. The two protons which had the four nucleons bounded together, proton neutron proton neutron. Okay, this proton neutron is disintegrate into a deuterium and a hydrogen. Deuterium having one proton and two neutrons, and a hydrogen having one proton. So do you notice one of the proton is broken, isn't it? So if this proton is broken from the original nuclei, what happens to its binding energy? The energy with which it was bounded inside the nucleus of the heavy nuclei, this extra energy is being released during the nuclear fusion reaction, and this extra energy release is the binding energy. And we know from where this binding energy comes from. This binding energy comes from the mass defect delta M. So if you have any confusion with this mass defect, I will refer you to go back to my previous video and check that mass defect again. Fine. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So thank you.